Hello, you're welcome. All right, so we are going to actually look at simple pendulum practical simulation. Okay, now one of the things that you should actually get to understand about physics practical is this. Okay, every physics practicals that you conduct is actually it's actually going to it's an investigation of a particular theory, okay, or law. So, and of course most of the theories actually it has formula um that actually forms the theory, or that is actually derived from the theory. Okay, so and those particular formula, right, is what validate that theory, if you understand what I mean. Now, let me actually illustrate what I mean. Okay, now let's see, this is a simple pendulum experiment, which of course you, in conducting this experiment, okay, you will be asked to actually um, to evaluate the period, okay, of the simple pendulum for the different lengths of the pendulum, right? So if you have actually conducted this, which of course I'm going to show you how to conduct it, and we are going to look at the theoretical way of actually getting the same value, okay, that we would have actually got if we do the actual practical. So when you understand how it works theoretically, then the practical will not be a problem. Okay, all right, so now you'll be asked to actually evaluate the period of the simple pendulum, and from theoretically the formula of the period of a simple pendulum is given as 2 pi, all right, the square root of L all over G. Okay, 2 pi t is equal to 2 pi the square root of L. So this is actually the formula. Okay, so whatever you're going to do here, it is this formula that actually this formula actually confirms that your experiment, okay, is correct, or is not your values, okay, are correct or they are not correct. Okay, so now, okay, so now let's actually look at how the experiment work. Now this is actually the setup of the experiment. This is the setup. In the setup of the experiment, okay, you'll be asked to the simple pendulum, all right, which is actually connected to a particular mass, a fixed mass, okay, using a string of a particular length. Now you'll be asked to vary the length of the string. Now, if you look at what you have from this formula, from the formula of the period of a simple pendulum, we can actually conclude that the period of a simple pendulum is directly proportional to the square root of the length. So which simply means that as you increase the length of this simple pendulum, the period you get, all right, is will also be increased. So now, how do you actually conduct this experiment? Okay, now you first of all measure the length of the string. Okay, then you now connect the pendulum to this retort stand, then displace it, just displace the pendulum a bit, then allow it to oscillate. Okay, so now the apparatus you're going to use for this particular experiment, the apparatus, okay, the apparatus which is needed for this for this experiment actually include, you have the retort stand, which I've actually shown you, the retort stand. Number 2, you will need a stopwatch to measure the time for a particular number of oscillation. Number 3, you will need a meter rule to measure the length. Okay, then of course you also need a fixed mass, of a particular, value, let's say 20 grams or so. The mass does not change. Okay, what actually changes is just the length of the pendulum. Okay, so now at the end of the day, you'll be asked to draw a graph. Okay, which of course you need to have a table of value. You need to create a table of value for your graph. So now I believe that you must have conducted this practical before, but I'm going to show you, okay, how you can actually conduct this practical without touching the practical instrument and still have accurate value. Okay, so now when you're asked to conduct the practical, of course you have to create a table of value. Okay, this is the serial number, right? And then which of course, let's say we are gonna have a reading for 1, 2, 3, 4, 5, let's say 6. Okay, for the different lengths. Okay, different length of the pendulum. So I can use that out in cm. So all the length of the pendulum in cm, I can, okay, let's start with 20 cm, or better still, start with 10 cm. Okay, I can start with 10 cm. 10 cm, is that too small? Okay, 20 cm. Okay, so from 20 cm we increase it to 30 cm, 30 cm, 40 cm, 50 cm, 60 cm. Okay, and of course I don't need to write the cm, or I've already indicated it, okay, at the heading of the column that these are all in cm. So let me clean up the cm. Okay, so and another thing too, I have to make sure that my precision, I have to indicate my precision. So my precision should be to 1 decimal place. Okay, okay, so now for each of this length, you'll be asked to find the time for 20 oscillation. Okay, you'll be told the number of oscillation. Okay, you might be asked to find the time for 20 10 oscillation depending on the structure. Okay, let's look at the time for 20 oscillation. So we'll measure that time in seconds, small letter t. Okay, measure that time in seconds. Then after you have found the time, you will also be asked to measure the period. The period, how you measure the period is you divide the time by the number of oscillation. Okay, after that you also be the period also is in seconds. It's in seconds. You have to atomize that. Okay, you also be asked to find the square of the period square. Okay, which of course is in seconds square. All right, so these are the values that you are required to take, okay, in conducting this practicals. Okay, so of course you need to arrange your table well. Okay, so now the question is, in the laboratory, let's say this is the practical I'm asked to actually conduct, and I have to, okay, take my readings and write this. Is it possible for me to use theoretical formula to get the accurate reading without conducting the practical? Yes. Okay, the answer is yes. So how do we do that? Okay, everything will actually boils down to the use of this particular formula. Okay, the use of this formula. So in this case now, instead of actually getting the time, okay, as you would have done if you are conducting the practical, getting time for number of oscillation, rather get the period. Okay, because the formula that we have is a formula for period. Okay, get the period for that particular length. All right, so now I'm going to get the period. So when I have the period, from the period I can get the time for that number of oscillation. Now in most cases you'll be asked to find T1, T2. It's still going to be the same thing. Okay, T1 is you conducting the same practical over again. the same practical with the same length, so it does not necessary. So the examiner that is actually marking this, okay, does not it's not the number of times you conduct the same practical to have the accurate value, okay, it's not his or her problem. Okay, the important thing is that the average of the t, okay, is actually correct. And by the time we actually use this method, okay, the formula method, then we can actually get the correct we're gonna have a valid value for our t. Okay, so first of all, let's get our period. So from this particular formula, okay, we're going to get period for each of the lengths. So the very first length I'm starting with is 20 cm. Okay, and don't forget you have to convert the cm to meters. Okay, so the length is 20 cm, and 20 is 2 meters is 0.2 meter. Okay, so let's put that in the formula. So the period is going to be equal to 2 times pi. That's 2 times pi. Pi is 22 all over 7, which is approximately 3.14. Okay, the square root of the length, which is 0.2, then divided by g, which of course is 10. Now let's actually do this. This is going to be 2 times 3.14, that is 6.28, then multiply by the square root of 0.02. Okay, 0.02. So at this point, I think we need calculator can actually help us, right? So I hope you're with your calculator. Okay, so here we go. So I'm gonna find the square root. Please pardon me. I'm gonna find the square root of 0.02. So where is my square root? Okay, here we go. 0. We can solve that. 0.02 times square root. All right, then I have to multiply by 6.28. Okay, so I have 0. Since I'm going with one decimal place, so I have 0.9 approximately. So the period at that point is 0.9. Okay, so the period is 0.9. Okay, so I want to get the value, and of course you can always do this in a rough. Okay, you don't need to actually tell the examiner that you didn't conduct the practical. Okay, it's not necessary for you to write, so you can just do this calculation in a rough, then put down your values. All right, so since I assume this is actually a rough paper, so I can actually clean it up and get my next reading. So the next reading, the length is 30 cm. That's 0.3 meter. Okay, and if I divide by, pardon me, so the period is going to, remember the period is the 2 pi is 6.28 first, then the square root of L over G, that is 0.0 0.3 divided by 10, which is 0.03. Okay, so the square root will be 0.03. Okay, so in this case now, calculator will help us do this work. Okay, please pardon me. All right, so I have 6.28. Then okay, let me do the square root first. 0.03 square root, then multiply by 6.28. Okay, so 1.1 approximately. So 1.1 approximately. 1.1 approximately. 1.1. Next reading, okay, L is 40 cm. That's going to be T is going to be equal to 6.28 times the square root of 0.04. Okay, let's do that. Okay, 0.04 square root. All right, then multiply by 6.28. So 1.3 approximately. 1.3 approximately. So I will have 1.3 here. Okay, I'll do the same for 50 cm. That's going to be 6.28 multiplied by the square root of 0.05. Okay, let's do that. 0.05 square root. Then multiply by 6.28. 1.4 approximately. 1.4. Let's put that down. Okay, 1.4. Okay, this, please pardon me. Let me do that again. Okay, yeah, 1.4. So here I have 1.4. And of course, for the graph, you have to take the line of best fits, okay? Or the point may not actually align well. So it's just going to be a line of best fits. Okay, so here we have the next, which reading T is going to be equal to 6.28 times the square root of 0.06. Okay, here we go. 0.06 square root, then times 6.28, 1.5. Okay, 1.5 approximately. Then finally, T is equal to the square root of 0.07. 0.07. Then 0.07. Then multiply 0.07. Okay, spell it, please. Pardon me. 0.07. Then we would now do the square root. Then now have to multiply by 6.28. 6.28. Here we go. 1.7 approximately. Okay, so 1.7. All right, so with this now this is really what is necessary. This column and this column, that's what's necessary. Okay, the two necessary columns, okay, are very important column. Actually remains the length, and the period square, right? Because this is what we're going to use for our graph. But you need to actually, from the instruction, okay, remember, if you're conducting a practical, you need the time for the number of oscillation, okay, to get the period. But now we are using theory, okay, so we are going the other way around. We need the period to actually get the time, okay. I hope you understand that. All right, so okay, here we go. So now for me to be able to get the time, okay, fill my time column, I will apply the formula. Okay, the formula goes this way: period is equal to time then divided by the number of oscillation. So that's gonna be time now is going to be equal to number of oscillation multiplied by the period. All right, so each of them, and let's the number of oscillation we're looking at, let's say 20 oscillations, right? So I'm going to multiply each of this value by 20. So 0.9 I'm multiply by 20. Okay, let's do that. 0.9 times 20. Okay, what do we have? So I have 18 seconds. Okay, so I will actually, okay, I will allow you to fill this column by yourself up. So let me not waste time. Let me get the square of my period so that I can draw the graph. Okay, so square of the period 0.9 square should give me 0.81 if I'm not mistaken. Okay. 0.81 second square 1.1 square all right 1.21 okay here we go oh the 1.3 square 1.3 square 1.69 then 1.4 square 1.96 1.5 square okay 1.5 square 2.25 then finally the last but not the least 1.7 square 1.7 square 2.89 okay so here is this is our reading then we'll have to draw the graph. Okay, after drawing the graph we are going to calculate the slope and I'm going to tell you the implication of some of the things that the implication of some of the parameters in the graph. Okay, so now usually you'll be asked to draw the graph of t square against the length. Okay, the graph of t square against them, that is being t in the vertical axis, then the length in the horizontal axis. Okay, t square against L, the length. Okay, so how do you draw graph? Because I'm going to show you how to draw graph in this video lesson. Okay, so how do you actually draw graph? Now, if you want to draw graph, first of all, okay, you have to take your scale. Now, how do you get to your scale? Because for the graph, okay, I believe I have graph here. Okay, so this is a graph. Let me actually clean that up. Now, each of these boxes, okay, each of these boxes in this graph is 1 cm, okay, it's 1 cm. So now, first of all, you have to actually designate your vertical axis, okay, and of course your horizontal axis. So my vertical axis is that is the period square axis, t square axis. So let me draw a line. Please pardon me. Okay, so let me draw a line to actually represent that. Okay, I don't think so. I'll have to delete that. Okay, I need. Okay, I need to get. Okay, here we go. So all the way. So now don't mind mine. Okay, you know, if you want to do yours, you have to use ruler. Okay, so this I'm using computer to illustrate. So yours have to be straight. Okay, and of course if you pass through the thick line. All right, so I will have to. This is for the vertical. I will have to also draw for the horizontal. Okay. All right, so as I said, yours should be better than mine. Okay, so now the horizontal axis is the L is cm axis, while the vertical for me is t square in second square. All right, so we need to actually write our scale now. How do we write our scale? Okay, so for you to get the scales, you need to know the value for the interval of these boxes, okay, or this rectangular boxes, the large one, the one that with the thick line. Now each of these boxes is 1 cm, so we need to know the interval for each of the axes. So you need to know the value that you're going to assign to each of these boxes, okay. So how do I know the value that I assign to each of these? So all I just need to do is to take the range, okay, the range of my value, that's the difference between the final and the minimum, then divide it by the number of boxes. That's how you do that. Okay, the maximum, please, I take the difference between the maximum and the minimum value of my t square. Okay, starting with t square. So the minimum value is 0.81 and the maximum value is 2.89. 0.81 and 2.89. All right, let's go to that graph. Okay, or better still, let me do that calculation here. Okay, so the difference 2.89 minus 0.81. Let's subtract that. Let's do that subtraction. 2.89 minus 0.81. That's 2.0, so that's 2 approximately. Okay, so now I have to divide it by the number of boxes that I will use, okay, in my vertical axis. Let's just count the number of boxes I have that's available for me. 1 2 3 4 5 6 7 8 9 10 11 12 13, okay, 14 approximately. So let's probably call it 10. Okay, 10, let's just call it 10. Okay, let's just call it 10 boxes, right? Okay, so that you can utilize the 10 boxes, just 10 boxes for your vertical axis. Okay, so if that being the case now, so I'm gonna have 200. What was that value again? Please pardon me. What was the value again? Okay, 2.0, right? Yeah, 2.0, approximately 2.0. So 2.0, okay, divided by 10 bucks. So each of the bucks should actually, it should increase by the interval of 0.2. Okay, 0.2 seconds. So now, if we are to write our scale now on our graph, let's write the scale on the graph. So after write the scale on the graph, I will now say that okay, in t square as this. Here's my scale. Okay, I will simply say that 1 cm 1 box, right, actually is gonna be equivalent to 0.2 unit, 0.2 seconds. So I can use unit. So each one, okay, at the interval of 1 box, I'll have 0.2. So I'm having 0.2. This will be 0.4. Okay, let me not write that. Let me write that behind, not inside my graph. So here 0.2. So I don't want to jump at the value, so I can skip this. I know this is 0.4. So this now should be 0.6. This is 0.8. So here I have 1.0, 1.2, 1.4, 1.6, 1.8. Okay, 2.0, 2.2, right, 2.4, then 2.6. All right, I am good to go. So for, let's take the scale for my horizontal axis. Okay, I am taking the scale for my horizontal axis. Okay, that's length. So my interval is from 20 to 70. So the difference is 70 minus 20. Right? The difference is 70 minus 20, which is 50. So how many boxes do we have? How many boxes do we have? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's probably approximate it to 5 boxes. Okay, so it should be fair enough. 5 boxes. So since there's 50 divided by 5, that's gonna be 10. So each interval I should have 10. Okay, so have 10, 20, 30, 40, 50, 60. All right, so now let's take that scale. So I will now say in L as this. Okay, I'm not supposed to be writing this. Of course, I'm covering my graph. Let me clean this up. I'm supposed to write this at the top of the graph. Okay. I need to write this here. Okay, so that it will not actually got to cover my graph. Okay, here we go. So in t square axis, okay, column, and I say that 2 cm 0.2 unit. Then here in L axis, 2 cm or 1 cm, that should be 1 cm, please pardon me. 1 cm, all right, is equivalent to 10 units, okay, or 10 cm. All right, so let's start with the graph. So here I'm gonna have 10, okay, 20, 30, 40, 50, 60, then 70, 80, so on and so forth. Okay, so let's start tracing our value. So now you need to know, now that's the big boss. Okay, you need to know the value for each of these small bosses so that you know exactly where to trace your coordinate. So how do we get the value for each of the small boxes? So how do we get the smallest, I mean the tiny box, the tiny intervals, okay? The small interval. And that small interval I think it should be 0.1, if I'm not mistaken. Let me count it. I have 1, 2, 3, 4, 5, 6. Okay, I think I have 6 in one. 1, 2, 3, 4, 5, 6, 7. Okay, okay, if you wish to do that. So that means the difference for 0.2, one boss is 0.2. Okay, so now divided by the number of lines, or number of the smallest units, okay, which accounted to be 7. Well, let's approximate it to, okay, let's approximate it to, let's say 8. Let's make it 8. Okay, so that I don't want to have a recurring decimal. So now I'm gonna have 0.2 then divided by 8. So I have 0.025. So each tiny line is 0.025. For this one here, the scale is 10 cm. 10 cm, then divide by 7 or divide by 8. Okay, 10 divided by 8, 1.25. So 0.25, 1.25. All right, so let's start tracing out. Let's start with the tracing of our points. Okay, so when the length is 20 cm, our t square is 0.81. 0.81. Okay, let's go to the graph. 20 cm, then I have 0.81. So this is 0.6, this is 0.8. So 0.81 is just a tiny line, just one line after, so above. Okay, so I'm gonna do that. I'm gonna trace that up to that point. So 20, I will get to, this is 0.8, this is 0.1, just above 0.8. Okay, so next reading. 30 goes with 1.21. 30 goes with 1.21. Okay, so let's get that. 30, 1.1, this 1.2, 1.21, just above 1.2. Okay, next 40 goes with 1.69. 40 goes with 1.69. This is 1.69 should be. Okay, just around this point. All right, so here we go. 50 goes with 1.96. 50 goes with 1.96. This is 1 point. 1.8. This is 2.01. Okay, 960 is just gonna be just below 2.0. Just below 2.0. And of course, it's gonna be approximate value. Okay, so it may not necessarily be on that point. Okay, the graph will be an approximate graph. Okay, the point may not really, okay, be exact, but it should be close. All right, and then finally, no, that's not the last. Okay, 60 goes with 2.25. 60 goes with 2.25. So this is 2.24. It's just above 2.24. Just above 2.24. Okay, and the last but not the least, 70 will have 2.89. 2.89. Okay, I think that will be this is 2.8. So just somewhere around there. Somewhere around. So I'm just going to put that around just here. Okay, so it look close to a straight line graph. Of course, you're not going to have a perfect straight line graph. Okay, so what you have is a line of best fit. So just join the line. Okay, here we go. Of course, you know that you use a ruler. Okay, something like this. Okay, so majority of the line actually passes through. So if you're able to draw this graph and you have this, then you are good to go. It is good. It looks, so don't forget to extend it to pass your vertical or the horizontal axis. Okay, you need to pass through the axis. So I have to extend it just in case you need to answer any question that is based on slope, on intercept, pardon me. Okay, so that's it. So I hope that's well understood. So other questions that you might ask to evaluate after you must have drawn the graph now is what I will show you now. Now other questions include finding the slope of this particular graph. Right? How do you find the slope? Okay. Now the very simple way, you can use your table to find the slope, or you can actually use the graph. The slope is simply the change in the vertical axis, okay, divided by the corresponding change in the horizontal axis. So how do I actually get the change? Okay, I can actually draw a line to indicate the change. I can draw a line, an imaginary line, to indicate the change from the place under me. Okay, so I can just draw an imaginary line to indicate a change. So just come here. Okay. Okay, here we go. Okay, the change again from this point to this point. Vertical change and of course the horizontal change. You can all right, so this is delta t square. and this is going to be delta L. Okay, so that t changes from this point, from this value to this, while L changes from this point to this point. Okay, so let's get this loop. Okay, so let's calculate this loop or the gradient. So here we slope change in the vertical axis, which is change in t square, divided by the change in horizontal axis, which is the change in L. All right, so change in t square from what we have here changes from this is 0.8 to 2.0, so that's going to be 2.0 minus 0.8. Okay, then for and now trace the change here. Now this line actually started from not 2.0 but below 2.0. That should be 1.8 approximately. Okay, and end at 5.0. Okay, the horizontal line, the change in L, 1.8 to 5.0. So just do 5.0 minus 1.8. Okay, so you subtract that, and I think here I'm having 0.2, and now in this case I'm having that should be 3.2 if I'm not mistaken. Okay, if I'm not 3.2. So you divide that, you will have this loop. Okay, but that's not the catch. Okay, now let me tell you where the catch is. Now still based on the theory, why was the graph t square versus L? Have you bothered why you were asked to draw the graph of t square? Why not the period versus the length? Why do we have to find the square of t? Okay, I will tell you. Now, the reason why you are asked to plot this graph, okay, is actually based on the equation of a straight line. All right, now let me tell you how that works. This is the general equation of a straight line. Okay, where this m represents slope, the c represents the vertical intercept. So the reason why you are being asked to plot this graph is that, okay, the reason why you're asked to plot the graph of t square versus L is because that formula for the period of a simple pendulum was actually converted to the equation of a straight line graph. Okay, it was converted, and I believe that one of the very first step in practicals, okay, physics practicals, is you should know how to actually convert an equation to the equation of a straight line. So I have to convert this now. For me to convert this to equation of a straight line, all right, all I just need to do, I have to square both sides. I'll square both sides. All right, so I'll square both sides. I have t square. So if I square 2, I'll have 4 square pi. I'll have pi square. Then if I square the square root of L all over G, I'll have L all over G. So as you can see now what I ended up now taking out the L being the independent variable, t square. All right, okay, t square is the dependent variable, while the L is independent variable. So invariably you are going to compare this with the equation y equal to mx plus c. Okay, the x here is the independent variable, all right, which is equivalent to the L, the horizontal axis. Y here is the dependent variable, which is equivalent to the t square. Okay, so if L now is equivalent to x, which simply means that the coefficient of x becomes the slope, right? So now what is the coefficient of L? Okay, I can also write this way. This is t square. I can separate the variable, separate the coefficient, 4 pi square all over g, okay, then L. So which simply means that if I should compare this to this, I can conclude that, okay, the slope is actually equal to, slope being the coefficient of x, okay, is going to be the coefficient of L. So, and the coefficient of L is 4 pi square. So, which simply means that the slope we got, the implication, if they ask you what is the implication of the slope you got from plotting the graph, the slope you got from plotting the graph is equivalent to, is equal to 4 pi square all over g. So in most cases, okay, after conducting the practicals on a simple pendulum, you will always be asked to find, okay, the acceleration due to gravity, because this is a pi is a constant, 4 is a constant. Already you have calculated the slope. Okay, by the way, let's actually get the slope so that we cannot get the acceleration due to gravity. Okay, so the slope is 0.2 divided by 3.2. Please pardon me. 0.2, okay, divided by 3.2. Okay, so I'm having 0.062, so 0.06 approximately. Okay, so my slope is 0.006 equal to 4 times pi square. That's 3.14 square. Then divided by g. So I can now get my g, okay? Right, so that's going to be, my g now will be 4 times 3.14 square all over 0.06. Okay, now let's do that calculation. 3.14 square, then multiply by 4, then divided by 0.06. Okay, so approximately 6.657. Okay, so now this 657 we need to actually we need to convert, because what we use in our slope here, okay, what we use in our slope here is seconds. Seconds is actually the SI unit, but the length is in, okay, the length we use is in cm, so I need to, this length need to be converted to meter. Okay, the length need to be converted to meter. Okay, so that's going to be 3.2 convert 3.2 cm to meter. That was going to be 0.032. Okay, so what I'm supposed to have here is going to be 0.2 divided by 0.032. 0.2 divided by 0.032. Okay, 6.25. So what I'm supposed to have here is 6.25. All right, so let me clean that. Let me clean up here. Okay, if I'm not mistaken. All right, so let's go again. So 3.14 square multiply by 4, then divided by 6.25. So that is 6.3 G. Okay, 6.3. Now, if you compare, remember the value of G is 9.8. Okay, which of course, due to experimental error, there's actually a kind of deviation. Okay, and of course, very if you conduct the practical from all this our graph and everything, taking this particular slope, we know that in taking these values, okay, there should be some experimental error, but if you do it very well, take your time. I'm only trying to illustrate. Okay, you should have a value. Your G should actually have a value that is actually close to the actual value of acceleration due to gravity. Okay, so that is that for this particular practicals. Okay, so we are going to look at more practicals in the next video. All right, so see you in the next video. Thank you very much.